Part 1. What is science? There is no single definition of the word science. There is debate on that issue. One definition is that science is a search for natural causes of all events. This first definition is imperfect because it has an assumption. An assumption is something that is unproven but is accepted to be true. It has an assumption that everything has a certain kind of cause, and this cannot be proven. Science is full of assumptions that are taken by faith. Most assumptions are agreed by everyone. Most assumptions are agreed upon by everyone on faith. So we have the faith that, hey, if we do an experiment where we drop a ball today and it hits the floor at 5 miles per hour, that we just have faith that tomorrow, if we drop the same ball under the same conditions, it's going to hit the ground at the same speed. And that the equations that work today, they're going to be working tomorrow. We just have faith that that happens. We can't escape some assumptions, and some are apparently perfectly reasonable. We must assume that gravity is going to work tomorrow just like it is today. But some assumptions are debatable. Some are not agreed upon. Most of the debates in science today are about whether or not an assumption is valid. When you have a debate, you better check each other's assumptions. A second definition is better. It is, well, let's get this in focus. The second definition is better. It's a little bit more simple. Science is a study of matter and energy. And that is the definition that we're going to go on in this class. So that's what science is. Now, what does science do? What can it do? The traditional ways of describing the steps of the scientific method are something like this. State the problem, make a hypothesis, do an experiment, organize your data, and make conclusions. Number 7. There are no official steps, though, to the scientific method. Here we have 1, 2, 3, 4, 5 steps. I've seen this broken down into as many as 13 steps. And there's lots of them in between. So there's no one way of saying it. The main idea of all these different methods is that the research is done in a way that's repeatable so that other scientists can check your work, and it's logical. So one thing naturally follows another idea. But this is not the only way of doing science. Can you do science without these steps? Yes, indeed. For instance, some ecologists spend a lot of their time just simply counting the population of a certain species. For instance, up in Canada, there are people that spend many, many days just crisscrossing the vast open areas with an airplane. They fly a little bit low so they can see things well on the ground, and they just simply count polar bears. And they keep track of where the polar bears are seen. And they just keep logs of this, and they keep maps. They're not doing any kinds of calculations. They're not doing any hypothesis about do they think it's going to be getting bigger or smaller. They are just simply counting. And that's still considered a type of science. Number 9. All researchers can use tools in their work. If a tool can't be used to observe and measure the topic in some way, then the topic isn't science. Number 10. We can describe science as using tools to make observation, and then the person makes models to explain these observations. Models can be equations, flowcharts, objects, or drawings. It's anything that can be used in order to help explain something to somebody else. Number 12. What can't science do? So this up here is what science does do. This is what it can't do. There is much that is done in earth science that is not repeatable. Much of the science is called historical science. It tries to come up with possible explanations of past events, but such explanations cannot be proved. Most of the explanations are based on assumptions that can't be proved. Remember, assumptions are things that can't be proved, but they're taken as true because you got to say one way or the other. You got to have some kind of a starting point for placing then other observations and conclusions. Now, this is we're saying that these explanations can't be proved. This is not to say that the explanations are illogical or that they're not possible. It's just that we can't prove that that is indeed what had happened in the past. So, example, what created the hills of Moraine State Park and the hills near Springfield? The geologists will say that it's caused by glaciers pushing. And most likely that is indeed the case, but we can't prove it. It is possible that people carried all this dirt in baskets and piled it up in long lines. There are archaeological sites where we're pretty confident that that is indeed what had happened. So maybe that's what happened with Moraine State Park. Probably not. But the idea is that we can't prove for certain that it was the glaciers. There are other possibilities. Science cannot study everything or answer every question. It cannot answer questions about whether something is good or bad, or if some action is right or wrong. So is a painting a good painting or a bad painting? It all depends on your values and your personal likes and dislikes. There is no instrument that we can take a picture of the painting and a little needle move between 0 and 10, rating it from good to bad. Whether it is a right or a wrong decision to sign a treaty, can't really have a scientific instrument take a picture of a treaty and decide if it's the right thing to do or the wrong thing to do. Whether or not we should sign a treaty is a value thing, not a scientific thing. Science could tell us what will be the effect if we sign the treaty, if we follow all of those procedures, what will happen to, let's say it's a climate change treaty. There are lots of different ones that have been proposed. The latest one has been called the Paris Accords. And science can tell us what will happen if we sign those Paris Accords, and if we change our factories, what will happen to the environment. If we change the way of life, how will that improve the quality of life for the animals and plants and the quality of the oceans and all of that. But it doesn't say if that's the right or wrong decision. You might think to yourself, well, it's obvious that if it improves the environment, therefore it's going to be a right decision. But you have to think about what's on the other side. What are we trading off? What are the bad parts of the effects? So you might think of the lack of economic growth. How many more people are going to be in poverty? How many more people will have lack of access to medicines and quality of life and all that kind of thing? And is it worth the change in our lifestyle for whatever change there is in the environment? In many cases, it might be obvious that yes, it is worth the effects on society to have the better environment. But what if the improvement in the environment is just teeny weeny itsy bitsy, but the effects on the society is huge and catastrophic? Now is it worthy of signing the treaty or not? That's where all the debate is. The debate is how much of effect will there be on society? How much effect will there be on the environment? And how do they balance, and which do we value more? And it's not necessarily a cut and dry thing. That's why there's such a big debate. Number 14. Remember that scientists have no more authority in this, in terms of right, wrong, good or bad, than any other person in dealing with these ideas. This is particularly important in today's world where medical doctors make announcements about economic and social issues. So we have doctors standing up in the summer of 2020 saying that we need to have these new laws and these new ways of living because of science. Well, that's not really the correct way of saying it. What science can say is, if we have these laws, and if we change society in these ways, then therefore we'll have this many cases of COVID, and we'll have probably this many people dying. That would be a fine thing for a scientist to say in the name of science. If we do this, then this will happen. But it isn't in the realm of science to say we need to do this. We value this outcome more than that outcome, so therefore we should do these laws. Because in some cases we are weighing something that we can't point an instrument at and make a measure of. How do you measure people's psychological health? How do you measure somebody's opportunity for advancement? How do you measure a lot of these things that we are giving up in order to have the effect on the pandemic rates? That is something that is based on values, and values are not scientific. Values can be different for different people, and that's where the debates come in. Once again, I want to make sure you understand that it's okay for these doctors to make their opinions known on laws, but when they speak on laws and regulations and ethics, they're no longer speaking as a scientist. They're speaking as just another human being with their own values and biases. Science is not omniscient. It means that science cannot know everything. An example of this is a universal negative. Like, let's say the statement of, there's no such thing as a purple penguin. That is not something that science can determine. Now, science can determine if there's a purple penguin. You just take a camera and record that. That'd be easy. But to say that there's no such thing as a purple penguin, that is not possible. Because you could look all over Antarctica with all the penguins down there, take a picture of every single penguin and not see a single purple one. But that's not proof that there's no purple penguins, because maybe purple penguins can swim really well and they tolerate warm weather really well. And so these purple penguins are on the beaches of Tahiti and Hawaii. Okay, so we take cameras all over the world. We put them on satellites looking at the Earth from all different directions at all different times, and we don't see a single purple penguin. That is still not proof that there's no such thing as a purple penguin, because maybe purple penguins also have gills, and they live underwater, and they never have to come to the surface to be taken with a picture. Okay, so now we get submarines all over the place, taking pictures of every square inch of the ocean. Still can't do it because maybe purple penguins are like gophers and they dig burrows underground. Okay, so now we have X-ray radar that can look through all the different layers of rock of the Earth all at the same time. Does that prove that there's no such thing as purple penguins? No, because purple penguins live on Venus. Or maybe they live in outer space in the middle of nothingness. Do you see what I'm saying? You can't prove that they don't exist anywhere. Okay, what's next? Science is not infallible. This means that science is not mistake-proof. Infallible means mistake-proof. Sometimes scientists just simply lie like any other human. There was a famous experiment done with mice. I don't know exactly how the experiment went, but it had to deal with white mice and black spotted mice. And for some reason, the experiment didn't turn out the way that the guy wanted, and so he actually took a magic marker and made spots on the mice in order to falsify his data. And there's other cases as well where scientists just simply lied when they made up their lab reports. Now, thankfully, a lot of them have been caught, but have we caught all of them? We don't know. Some of them might be really sneaky and really good, and they've gotten away with it. Sometimes they're just simply wrong. For years and years, we were told that we need to reduce the amount of salt. Otherwise, a healthy person might turn sick. We've been told that you better not eat a lot of eggs because otherwise a healthy person will turn sick by having hardened arteries and such. High cholesterol, don't you know? Some people were told, hey, in order to stay healthy, you better cut out the dairy fats. And pretty much everybody agreed upon these things. But then, in recent years here, within your lifetime, we've found out that all of those are not true. Unless you are sick, you can put a lot of salt on your French fries and you'll be okay. It's only people who have other conditions that need to reduce their salt. Eggs, they were once saying don't eat eggs because of the cholesterol, but now even the government is saying, yeah, you can have eggs. That's okay. And they're saying that you actually need some dairy fat. So if you drink only skim milk and only low-fat dairy products, you aren't getting the nutrition that you need from these dairy fats. So those are 3 examples of when science has been wrong. And there's lots of other examples throughout all different areas of science. Chemistry, earth science, geology, all sorts of places. Here's a quote from an article that I got from the web. The peer review process guarantees little in terms of trustworthiness, even before political agendas compromise the issue. And yes, scientists can be very political and can use their numbers in mischievous ways to prove a political point. When studies were replicated, they rarely came up with the same results. Only a third of 100 studies published in 3 top psychology journals could be successfully replicated in a large 2015 test. So when you see a single journal being quoted in the news, they say a new study came out that proves that such and such makes such and such. There's only a 33% chance that if you did that experiment yourself, it would come up to be the same thing. That's almost like saying there's only a 33% chance of that report, that study, being accurate. It's more likely that it's wrong than being right. And that's true for medicine, epidemiology, which is the study of epidemics, population science, nutritional studies, and all sorts of other ones. Now, this is not to say that science should be ignored. I don't believe that. This is not to say that science is a lousy way of thinking. I don't say that at all. I still think that the scientific method is the best way of learning about the universe. I'm just saying it's not a perfect way. So here we say that only a third of the studies come up right with psychology. So what that means is before we make policy decisions, before we make rules and regulations and laws based on these scientific studies, what we need to do is have lots of studies come up with the same conclusion. Don't just trust one, but look at a whole dozen, 3 dozen, 100 studies, all done in different, slightly different ways, with slightly different subjects, and see what the conclusions are of the whole group. And then we'll come up with a better understanding. That would be much more reliable than a single study at a single time. Okay, debates in science. To continue with this idea of things being infallible, science is never settled. No idea of science is above criticism. Any idea can be proven wrong if the data goes against it. The number of scientists that believe something is not proof that it's true. In other words, even if 99% of scientists believe something, that doesn't mean that it's the actual fact. It could be wrong. Now, if 99% agree on something, yeah, we should probably follow it. That's probably good advice. But that doesn't mean that we can't challenge it in the future. If we come up with new data that is really hard to disprove, this new data might force us to change our ideas of what we thought was settled. If proven data, something that's shown over and over, if that contradicts a scientific law, then the law needs to be changed, rewritten, tweaked. And some laws have been changed dramatically. For instance, we once thought that in reactions, matter can never be destroyed. If you start off with 3 grams of stuff at the beginning, you're going to end up with 3 grams of stuff at the end. You cannot destroy matter in reactions. And that was settled science for hundreds of years, until about the year 1900, right about there, give or take a little bit, when we found out about nuclear fusion and nuclear fission. And in those processes, some matter is actually lost, and it disappears into energy. So you start off with 3 grams of reactants at the beginning, and you only end up with 2.9 grams of stuff at the end. A very small amount of stuff actually disappears. And so they've had to change the laws that they once had about reactions. Scientific debates now need to focus on data. First of all, when we debate things, we can't say that things are settled. Anything can be debated. And when we debate things, we better debate them based on the data, the process, the materials that were used. What we should not do is debate on name-calling, threats, claiming superiority. And unfortunately, oftentimes that's what happens in scientific debates. They should focus on data, but they end up focusing on name-calling each other, threatening each other, that kind of thing. We must be open to discussing data, even when it is leaning against our argument. Refusing to discuss data is very illogical and unfair and will not end up helping your side in an argument. If your side of the argument will still be damaged if you rephrase that. Your side of the argument will still be damaged if you avoid the contradictory data, so you might as well investigate it and attack the data. Or perhaps you will change your position and therefore be seen as a smarter person, because, smart people change their ideas when faced with better information. If you have a discussion with somebody and it turns out that they don't have good data, therefore they've come up with a bad conclusion, if you show them really good data and they refuse to even look at it, do you consider that person a smart person, or do you consider them pretty stubborn and not so smart? Well, if they refuse to consider good data, then I would not consider them a good debating opponent, and I would just refuse to even go there. And I would not look very favorably upon their position, and I'd be even very less likely to change my opinion to their side if they have such a stand. So lots of things in our society today are being argued, and we need to look at the data for those arguments. Otherwise, we're not doing a good job in debating. We're not going to persuade anybody. All right. So, the next thing we need to do is discuss this SLO business. The SLO is a special kind of a quiz. We take it 3 times. We take it once in August during the first week of school. We take it again in October after we've learned some information. And then we take it again in December at the end of the semester. Now, it's the exact same quiz, the exact same words in all 3 times. And in August here, we have not learned much science at all. This is our first day of notes. Well, you haven't been taught any of this stuff that's on our SLO here this week. I have not taught any of it in this day's lesson or previous days. So I do not expect you to know much of it at all. You might have a good guess on a couple of them, but I expect an awful lot of papers to be turned in completely blank, and that is completely okay. I'm not going to call home and say, oh man, your student did a really bad job, we're in trouble now, we got to do some tutoring. Nope, I'm not going to do that at all. The adults in your house will not be shown these numbers. As far as I know, I've never done it in the past. I don't think I'll ever do it in the future. There's no reason for it. It's a pre-test. It's not been taught before. You're not expected to know all of these things. You will not be penalized. Okay, now, we'll start learning this stuff starting right away with the next packet. Starting on Friday, I think. And we'll learn it over many weeks. And then in October, after you've been taught all of it, we'll take the exact same test again. And all we ask is that you make your way halfway up to 100 in this case. So in other words, if in August you get a 0, in October we want you to get that up halfway to 100, which is 50%. A 50% then would be passing. If you scored a 20% in August here, halfway between 20 and 100 is 60. So if you got a 20 on it this week, we'd expect you to grow halfway to 100 up to 60% in the October setting. So that would be your passing grade there. If you scored a 40% this week, in order to get a passing score in October, you'd have to get up to a 70%, halfway between 40 and 100, and so on. So your passing score in October depends upon how well you do this week in the pretest. If you get this passing score, whatever it may be, it's different for each person. If you get this passing score, then you get a grade of A+++, a 100, in a 5% category for your overall grade. If you don't get this passing grade, then you just don't get the 5% A++. Then your class average is just based on your other quizzes and your homework and your projects, not the SLO at all. Okay, now, if you don't get this passing score, whatever it may be, in October, then we have a couple months here to get more tutoring between October and December. And hopefully in December, when you take it, you'll get either the 50% passing or the 60% or the 70% or what have you, whatever it is, halfway between your score here in August and 100. But it's the same number, October, December, that you're aiming at. You don't have to get an even better score in December just because you had more time to learn it. It's the same benchmark that you have to meet according to what you got in August. Alrighty, I hope that describes the SLO well enough. So you can think of different strategies that you might want to use for this. You might want to talk it over with your friends as to what's the best way to do SLOs. Okay, that is the end of our notes here. What you need to do is do wrap-up number 4 and anything else that the teacher talks about. We had a black box activity if we had class time work. If there was a snow day or e-learning, then we did not do the black box activity. You can scratch that off. Just do the wrap-up number 4 and anything else that's on the web in the Schoology folder for lesson number 4. Please confer with today's materials there. Follow any directions that are in Schoology.